Hi, we're Team 14, and we're going to present our work, Soft Robotics for Tactile Object Classification. So some background on the problem. Soft robotics is a really growing area of research right now because it allows robots to deform on contact and increase their safety with their environment. Within soft robotics, our area of focus is on manipulation, so robots touching what they're interacting with, and specifically we're working on tactile manipulation. So in low light conditions or when the gripper is obscured from a camera, you might not be able to see it, so it's important to be able to touch. There's a lot of prior work in this area using a combination of different sensor types or multiple sensors and different deep learning architectures like CNNs, transformers, and LSTMs, but our goal is to use just one sensor.
So our goal is tactile object classification using a single embedded position sensor, which reduces the sensor count, which lowers the cost and the failure risk. Our system used a capacity band sensor for position feedback, for SMA actuator for the deformation and the motion, and a silicon body for compliance. We are aimed to extract the useful tactile data with the minimal hardware. Our dataset, we created a custom dataset with 7 different objects, 30 trials per object, total of 15 hours of interaction data. Objects are vary in shape, texture, and stiffness.
So we have a script that will control the finger, and it will follow a waypoint-defined trajectory to interact with the object. This keeps interactions consistent between trials and different objects, and we perturb the object location between trials for variation in the data. From this, we extract a 9 degree of freedom time series data with the position, target position, the waypoint index, and then power inputs to each of the SMAs. This is to give an idea of what our data looks like. So on the left, you can see position and target position data. And then on the right, we have the power input to each SMA.
Many prior works use statistics as handicraft features, so it forms a robust baseline. Since our data are separated into multiple waypoints, we collect both per waypoint statistics as well as the overall features, and then put it into a 2-layer MLP. We also use some multiprocessing library to pre-calculate the features to fasten the training.
So our first data augmentation approach is split each trial into the windows of the set length and ignore the data points with less than 0. Why is less than 0? Because we don't need those kind of information in our data set. We also add the enhanced features such as X delta, Y delta, error signals, magnitude, and the PWM signals. And lastly, we add the augmentation for like a random noise, time wrapping, feature masking, and data normalization.
So our first advanced deep learning method is a CNN, where we feed in our 9 degree freedom time series data. We have 3 1D convolutional layers with batch norm and ReLU, average pool and flattening layers, and then 2 fully connected MLP layers, followed by a softmax, which gives the class labels. We're also working on RNN and transformer architectures. For the RNN, we add a bidirectional LSTM layer into our CNN classifier. And for the transformer, we use 4 convolutional layers followed by ReLU and batch normalization with 2 transformer encoder layers. So in terms of results, our performance metric is classification accuracy. Since we have 7 classes, we would say the naive baseline would be the random guess, and with 7 classes, that gives about a 14% chance of a correct result. With the smart baseline based on statistical features, we're getting about a 47% accuracy. Then our best result is with the CNN, which is a 51.3% classification accuracy. So more than 3 times better than guessing. So to go into our best result a bit, we present the confusion matrix on the right. You can see that the objects that were most easily classified were the blue ball and the pink ball. These objects had the most unique stiffness, so these were the softest objects by far in our data set. So that we think that the CNN was able to pick up on some of those textural features.
To further enhance the model, we add transformer encoder layers after the CNN layers. The intuition is that after CNN extract the local spatial patterns, transformers hopefully can capture the long-range dependencies. The best feature aggregation we use is the classification token method, which is better than the min pooling and the max pooling.
So in conclusion, we show that deep learning offers significant improvements for object classification. Our current best result is greater than 3.5 times better than random guessing. CNNs so far are also the most effective at differentiation, especially regarding stiffness. And this has applications in robots operating in dark environments or where the camera would be obscured. Our next steps are to continue developing our transformer architecture and to explore ensemble methods combining different models that we've developed so far. Thank you.